Living beside the ocean has given me an opportunity to play in the water many, many days. The power of these waves is incredible. In this video, we're going to look at moving waves. So behind me, you can see my pendulum here swinging. And we've looked at how the mass and the angle of the pendulum don't influence its period. What we do know is that the length will change things. So, what many mathematicians or scientists have done is they have made measurements around a pendulum to try and graph how it would move. So, I could measure the angle every second, I could measure its change in height, or I could measure its change in distance. And the one that's probably the easiest to measure is the side to side because it's got a lot of movement side to side. And so if I made a data table and graphed it, what would it look like? I have my pendulum drawn here in blue with my rest position with the dotted green line. If I was to release that pendulum, it would swing over and then it would be over here. And then what would happen? Well, it would then swing back. And if there was no friction and perfect conditions, this would keep going forever. So as we mentioned before, is that we could make a data table. And let's say I measured the time, or I didn't measure the time, but if I took after certain amounts of time, let's just say we depends upon how long that string is, we could record the time here and the distance that it travels side to side, right? My distance side to side. There's many ways we could record this. I'm going to call this my zero position here. And let's say that this is, I don't know, +1, and let's say that this is a -1 over here. So where was it when I released? Well, it was over here at -1. And what happens is that it gets less and less and less, and then at some point in the future, it's going to be at 0. And then sometime further in the future, it's going to be a +1. What happens then? Well, then it's going to start to swing back, and it's going to go back to 0. Then it's going to go back over here to the -1. And then what's going to happen? Well, it's over here. It's going to swing back. It's going to go back to the 0, back to the +1, and then it's going to repeat. So if I was to graph this, and I don't have, beautiful data here that we could do, but we could do that data if we wanted to. So I could take my graph, draw my coordinates here. This would be my distance in centimeters. This would be my time that I measured it with seconds. And where did I start with this one? And it didn't matter. I mean, I could have started my pendulum in the middle at the rest. I could have started on the right side where I called +1. But it doesn't matter. For this example, I started it here at -1. And then a short time later, it was here. And then another short time later, it was at +1. And then it went down to 0. And then back to -1. Back to 0, up to +1, back to 0, down to -1. And what we have is we have this pattern. And this is a wave function. So the pattern that we get when we graph the position of the pendulum, it will oscillate. It'll go up, it'll go down, it'll go up, it'll go down. That's the graph. But what really is happening is the pendulum's moving side to side. This time, instead of having a pendulum swinging side to side, I have a spring going up and down. And it oscillates. And if we were to graph its position, height versus time, I wonder what we would get. And if you've predicted that it would be another wave curve, you're probably right. Start. Here I have one of my oscillations, well, a couple oscillations graphed, and there's so much information in this graph, and we need to understand a few things. So once again, on my x-axis is the time measured in seconds, and along the y-axis is the height in centimeters. And what we can see is that this graph was started from my rest position because it's in the middle. Okay, the previous one I drew, we started at the bottom, which was over on the left of the pendulum. And we can see that this goes to a height of 2 centimeters. So let's just assume here for a second that this was done from a spring, and we started in the rest position. And then what we did is we went to a height of 2 centimeters. So it depends which we call the positive and negative direction. But basically what I've done is I've pulled this down 2 centimeters. And so my distance increased 2 centimeters. And that's what this height here of my curve represents. This is called an amplitude. This is the amplitude. And that relates to the distance that my spring was displaced. Likewise, if I was using a pendulum, it would be equivalent to saying that I moved it 2 centimeters to the side. And you'll notice that this is in the positive direction. So whatever you indicate as your positive, here I'm saying it went down, but it increased by 2 centimeters. Then it returned to its rest position, and that would be my pendulum swinging back, or my spring returning, oops, not there, but my spring returning to its rest position. And that's the rest position right there. And it took 4 seconds to get back to its rest position. Well, then what happened was my spring then squished up 2 centimeters, or my pendulum, after it returned, it went this way 2 centimeters. And you can see that that is now at negative 2 centimeters. Once again, this is equivalent to the amplitude. I'm just going to put A there. So the amplitude is the height each time. It's not from the bottom to the top, as some students want to do. It's from the midline or the rest position to either the bottom or the top. It then returns to its rest position, and right here, it has completed one oscillation. So that's one, I'll use the word cycle this time. It's gone one cycle, 8 seconds. Okay, so our period is 8 seconds. That means our frequency is 1 over 8, which is what, 0.125 hertz. And what that's saying is that in 1 second, it's gone through an eighth of the wave. Okay, so it's gone this far. It's gone this far in a second, because it took 8 seconds to get to here. Okay. We can see that it then goes through a second oscillation or a second cycle. So what we have here is this. I have n is 2. So I found that n is 2. I found that my amplitude was 2 centimeters. I found that my period was 8 seconds. I found that my frequency was 1/8 of a second. And the last thing we haven't talked about yet is something called wavelength. And the wavelength is how long is one wave. Okay? To do that, we need to pick a place on the graph or on the curve. And how about if I go from here and find another place where it's equivalent? So I could go from, say, here to here. This distance right here is a wavelength. I could have also gone from, say, here, it's on the way down, to here is also one wavelength. I could have gone from the bottom here to the bottom here. That is one wavelength. Wavelength is frequently represented by that symbol, and it is lambda, another one of the letters of the Greek alphabet. So once again, to summarize, from this graph, I could tell number of cycles, I could tell my amplitude, I could determine my wavelength, I could determine my period, I could determine my frequency. Next up, what we're going to do is we're going to calculate or combine these things and determine how fast would a wave move side to side. Playing with springs can be a lot of fun. Here I have a big spring stretched out across my floor. I'm going to give it a little impulse here, and let's see what happens. I'm going to create a wave. Did you see the wave move? The energy that I gave the spring in my wrist is transferred, creates a wave, and the wave travels across the room. It hits the desk or the table that it's secured to, and then it comes back at me. Now, it's losing energy because there's friction between the floor and the spring. If I could hang one of these from the ceiling across the classroom, it would be much better. Let's go one more time. Waves tend to move or transfer the energy. You got to remember, this movement is the transferring of energy from one part of the wave to another, or from the spring to another. And it tends to move in one of two ways. The wave that I just did, where it's going side to side, is a transverse wave. I'm going to try a different one now. Instead of going side to side, I'm going to squish the slinky together, or the spring together. I'm going to make a bunch of coils here all together. And what happens when I release it? Did you see the expansion kind of moved? The energy of the squish passed it along. Let's see if we can see that again. You're going to see the coils of the slinky gather and disperse right across the entire length of this. And it traveled up, it hit the table again, and came back. Let's do a little bit more of a squish this time, see if we can really get a big one. When the energy is transferred down through the spring, it is referred to as a longitudinal wave. So we had our string or slinky stretched out. And what I did is I gave it a little shake, and this created this impulse that created this wave, or this little indentation. And over time, this wave, this indentation, moved down through the slinky. Okay? Once again, this is referred to as a transverse wave. The second type of wave that I created was when I pulled part of the slinky together. So I ended up with a couple of them really close together, but then they were all spread out. And what happened over time is that the condensed part moved. And so once again, we have this transference of energy down through the slinky, and it moves as a wave. And this is known as a longitudinal wave. When these are drawn, here's an example of what it looks like. Okay, so the longitudinal waves, you can see the condensed part here, here, and here. And our wavelength, lambda, this is our wavelength right here. In the transverse waves, this is our length here. Okay. Going back to our kinematics unit, we remembered that our speed or our velocity is the change in distance over a change in time. And that is true for our waves as well. The velocity in which it moves is the change in distance. But what we use is we use our wavelength. And our time is the period. But it's more commonly written in terms of frequency. So if you remember that our period is 1 over the frequency, or I could say that the frequency is 1 over the period, that means that our speed of one wave would be equal to lambda times the frequency. So that is our wave equation. That is how we calculate the speed of a wave. So for instance, if we had a wave that had a wavelength, so here we go, let's just say we have a wave here, and let's say that this is at, I don't know, 6 centimeters, and this is at, let's say, 10 centimeters, we would know that our wavelength is 4 centimeters. And let's say that we knew that our frequency was 0.5 per second. Then we would know that the speed of that wave, and we know the direction because we can see that it's moving to the right, the speed would be 4 centimeters. Wow, we should change that into meters. So that would be 0.04 meters multiplied by 0.5 per second. And that's going to give us an answer of 0.02 meters per second. Or we could write it 0.02 meters per second.